The paradox of information loss in the universe is one of the most profound challenges at the intersection of quantum mechanics and general relativity. At its core, the paradox arises from the apparent contradiction between two fundamental principles. On one hand, quantum mechanics tells us that information about the state of a system cannot be destroyed. On the other hand, classical general relativity, particularly in the context of black holes, seems to suggest that information swallowed by a black hole is lost forever when the black hole evaporates via Hawking radiation. How does this contradiction come about? Consider a black hole. According to Stephen Hawking's theory, black holes emit radiation due to quantum effects near the event horizon. Over extremely long timescales, this radiation causes the black hole to lose mass and eventually evaporate completely. If the process were entirely random, then the detailed information about the particles that fell into the black hole would be irretrievably lost, violating the principle of information conservation in quantum theory. Can we really reconcile these two views? This question has fueled decades of research and debate. Various theoretical models have been proposed to resolve the paradox. One prominent idea is the Holographic Principle, which suggests that all the information contained in a volume of space can be represented as a theory on the boundary of that space. In the context of black holes, this means that the information about everything that falls in might be encoded on the event horizon itself, and then gradually released with the Hawking radiation. This framework is supported by the ADS/CFT correspondence, a conjecture that relates gravitational theories in a higher dimensional space to quantum field theories on its lower dimensional boundary. Could this be the key to understanding how information is preserved? Many physicists believe it provides a promising route, though concrete proof remains elusive. Another intriguing proposal involves the idea of black hole complementarity. According to this concept, an observer falling into a black hole and an external observer may have different accounts of reality, but no single observer will witness a violation of quantum mechanics. From the outside, information might appear to be lost, yet from the viewpoint of an infalling observer, the information is preserved in a way that remains consistent with quantum principles. Does this mean that information is both lost and preserved? In a sense, yes. It's a matter of perspective and the limitations of our current theories in merging quantum mechanics with gravity. More recently, some have suggested that the resolution of the paradox might involve the concept of firewalls, hypothetical structures at the event horizon that could disrupt the smooth flow of Hawking radiation and encode information in a radically different way. However, the firewall proposal itself is highly controversial, as it challenges the notion of a smooth space-time near the horizon, a cornerstone of general relativity. In summary, the paradox of information loss in the universe forces us to confront the limitations of our current understanding of physics. It challenges the conventional wisdom of both quantum mechanics and general relativity by asking, how can information be conserved if it appears to vanish into a black hole? While the holographic principle, black hole complementarity, and even firewalls offer possible explanations, none has yet achieved universal acceptance. As researchers continue to develop new theories and test them against observations and experiments, this paradox remains a driving force behind the quest for a unified theory of quantum gravity. Could resolving this paradox not only answer a fundamental question about the fate of information, but also open the door to a deeper understanding of the universe itself? The ongoing debate and exploration indicate that the final answer may hold transformative insights into the very nature of reality. The information loss paradox arises from the apparent conflict between quantum mechanics and general relativity, where information about a physical system seems to disappear when matter falls into a black hole. According to quantum theory, information must be preserved, yet black holes appear to erase this information as they evaporate. This paradox challenges our understanding of how the universe fundamentally stores and processes information. Resolving this conflict is critical for a unified theory of quantum gravity. Astronomical observations of black hole evaporation via Hawking radiation suggest that as black holes lose mass, the information about the infalling matter might be lost, contradicting quantum principles. It's like watching a shredded document being burned. While the paper disintegrates, you expect that the message should somehow be preserved, but it seems to vanish entirely. Black holes, regions of intense gravity, seem to capture all matter and energy, including the information encoded in them, leading to the question of what happens to that information. Classical general relativity predicts that once information passes the event horizon, it is lost to the outside universe. However, quantum mechanics insists that information cannot be destroyed, creating a deep theoretical conflict. The study of black holes therefore becomes a key battleground in understanding the nature of information in the cosmos. When a star collapses into a black hole, its detailed physical state appears to be obliterated, raising the question of whether its information is truly lost or somehow encoded in the radiation emitted later. It's like dropping a secret message into a black hole like Shredder. You know the message existed, but it seems to vanish without a trace. Hawking radiation is a theoretical prediction that black holes emit radiation due to quantum effects near the event horizon. This radiation implies that black holes can gradually lose mass and eventually evaporate entirely. The key question is whether the Hawking radiation carries away the information of the matter that fell into the black hole. The debate centers on whether this process is unitary, meaning it preserves information, or if information is irretrievably lost. If a black hole evaporates completely over billions of years, the radiation it emits might encode subtle hints about the initial state of the infalling matter. It's like a slowly melting ice sculpture that might, in theory, release tiny droplets carrying a trace of its original form, though it's unclear if the complete structure can be reconstructed. Quantum mechanics is founded on the principle that information about a system's state is conserved over time. This fundamental tenet conflicts with the notion that black holes could permanently erase information. The challenge is reconciling the quantum requirement of information conservation with the seemingly irreversible process of black hole evaporation. Resolving this tension is essential for developing a coherent theory that unites quantum mechanics and gravity. In quantum computing, every qubit's state is tracked and must be preserved, illustrating the strict adherence to information conservation. A black hole appears to violate this principle on a cosmic scale. It's like having a detailed log of every step in a recipe that must be maintained. If a process seems to erase part of the recipe, you're left wondering how the final dish was made. The holographic principle suggests that all of the information contained within a volume of space can be represented as encoded data on the boundary of that space. This idea provides a potential solution to the information loss paradox by proposing that information swallowed by a black hole is stored on its event horizon. While this principle is mathematically compelling, it remains a subject of debate and ongoing research. Its implications extend beyond black holes, offering insights into the nature of space, time, and information in the universe. Theoretical models imply that the details of matter entering a black hole may be encoded in a two-dimensional form on the surface surrounding it, preserving information even as the black hole evaporates. It's like a hologram that encodes a three-dimensional image on a flat surface. The full picture is preserved in a seemingly simpler form. The firewall controversy is a proposed resolution to the information paradox that suggests a violent boundary, or firewall, exists at the event horizon, burning up infalling matter. This idea challenges the traditional view of a smooth event horizon and raises further questions about the nature of space-time near black holes. Critics argue that firewalls conflict with the equivalence principle, a cornerstone of general relativity. The debate over firewalls underscores the complexity and unresolved nature of the information loss paradox. Some theoretical models predict that if a firewall exists, any object falling into a black hole would be incinerated at the horizon, potentially releasing information in an uncontrolled manner. It's like expecting a gentle doorway to a room, but instead finding a wall of fire. This abrupt barrier forces you to rethink how passage and transformation occur. Several alternative models have been proposed to resolve the information loss paradox, including ideas involving quantum entanglement and modifications to general relativity. These models are critically evaluated through mathematical rigor and attempts at experimental verification. While each model offers intriguing possibilities, none has yet achieved universal acceptance in the scientific community. Critical analysis of these models is ongoing, highlighting both their strengths and limitations. Some proposals suggest that subtle quantum correlations in Hawking radiation might encode information, yet experimental confirmation of these correlations remains elusive. It's like trying different keys on a locked door. Each key may seem promising, but only a thorough test will reveal which one actually opens the door. The information loss paradox has significant implications for the thermodynamics of black holes, including the concepts of entropy and temperature. If information is truly lost, it would violate the principle that entropy should remain consistent within a closed system. Resolving the paradox is crucial for understanding the thermodynamic behavior of black holes and, by extension, the evolution of the universe. Discrepancies in predicted and observed entropy levels of black holes drive theoretical investigations into how information might be preserved or transformed. It's like trying to balance a checkbook. If money or information appears to vanish without explanation, you must reevaluate your accounting rules to ensure consistency. Future research on the information loss paradox aims to integrate more precise observational data with refined theoretical models to better understand the interplay between quantum mechanics and gravity. New technologies such as advanced space telescopes and quantum sensors may provide further evidence regarding the behavior of black holes. Continued interdisciplinary collaboration is essential to resolve this paradox and possibly uncover new physics. The outcome of this research could lead to profound changes in our understanding of the universe's fundamental workings. Upcoming experiments and observations are expected to offer more detailed insights into Hawking radiation and the potential mechanisms for information preservation. It's like upgrading from a blurry photograph to a high-resolution image. The clearer picture may finally reveal the details needed to solve the mystery.